In the last two activities, we've solved problems relating with quantifying and adjusting the gain in order to achieve gain margin and phase margin. We did that first analytically, and then we used the Bode plot command in MATLAB to quantify these a bit more empirically. And now in this activity, we're going to be using MATLAB's sisotool. And you're really going to love this tool because it makes a lot of this quite straightforward and does a lot of the work for you. At the same time, it's always important to remember exactly how it's doing that so you can always do it yourself. So this problem, similar to some of the ones that we just did, we're going to be quantifying the gain margin and phase margin for a complex transfer function and for a given gain value. In this case, we're going to be just using the gain is equal to 1. And then we're going to retune the gain. And in this case, we're solving a slightly more tricky problem where we're having criteria both on gain margin and phase margin. And so it's useful just to figure out which gains satisfy the gain margin criteria and which values of gain satisfy the phase margin criteria. And then we find the overlap between those two. So go ahead and open up the sisotool and use it in order to quantify these things and then retune the gain. That is just entering sisotool and then parentheses. So just like the RL tool, our transfer function model, comma the controller model. And so in this case, we're just doing proportional control. And so that is just a 1. All right, so I've opened up the sisotool for this example, and so you can see immediately over here in the Bode plot that it is already presenting you with the gain margin and the phase margin. And so again, when we look at the gain margin, this is identifying the locations where the phase is crossing minus 180. And so that crossing is then being traced up to identify our gain margin value. And likewise, wherever this is crossing the 0 dB line, that's coming down here and identifying the frequency where we're measuring our phase. And so here we don't even have to quantify it, but we could measure it. We could show our grid. And so here this maybe helps you estimate it a little bit more. This one is a little less ideal for grabbing points along the curve, and so that's why this is already showing it for you. We can notice though in this example, if we zoom in right here in this spot, we can see that we actually have 2 more 0 dB crossings right here and right here. And so that's happening at about 9.5, 9.6, and again here at maybe 9.7 or so. And so those are happening real close to each other. And so those would give you 2 more phase margins to investigate. And so if we look at what the phase margins there would be, we can see that these values are going to be roughly around, so minus 135. So it's a bigger phase margin than what is being quantified at this lower frequency value. And so just like when we saw it in the previous example, we wanted to find places where when we quantified either the gain margin or the phase margin, if there are multiple options for those, this again is which one is closer, because we're worried about which one is being essentially making it so that any small perturbation or change in the gain may end up making the system unstable. So whenever we're looking at multiple phase margins or multiple gain margins, we're always looking at the smallest one to quantify, smallest absolute value in order to quantify the one that we'll use for our actual phase margin. So that's why we're selecting this one, which happens here, rather than the 2 that happen over here. All right, so we already see that it's giving us the phase margin, gauge margin, so we can move on to the second part, which is identifying when the gain margin is greater than 5 dB, which we are not right now. We're only at about 2 dB, and then also where the phase margin is above 30 degrees. And so we actually already are above 30 degrees, so that's good. So remember, we're operating in proportional control, so the only degree of freedom that we have is to adjust the gain, and so that means we're going to be increasing or decreasing. So you can see as I pull this down, my gain margin is increasing, and so that's good. And so what I can do is, if I keep going, that just gets better, but if I were to push it up, we then get smaller and smaller gain margin, and so that becomes a problem. And so what we want to do is identify that location where this gets close to 5. And so this is where you have to fiddle with the mouse a little bit, but let's call that close enough. That's 4.77. So what we're observing is, in that case, the gain is somewhere around 0.7, 0.73, something like that, in order to make this at least gain margin of 5. And if we see, as I decrease this, anything smaller than that will also work. So we're looking for anything that's essentially below 0.7, 0.73. But we notice that now we've been messing with our phase margin, and so now we need to identify what values of the gain satisfy this phase margin. So you notice as we're increasing this, as I'm increasing the gain, I'm getting better and better phase until I jump over here. So notice now we've switched which 0 dB crossing results in worse phase. So up until some point, we get some good behavior. But you can see here we're getting well over 30. And so what we need to do is identify, so now we're below 30 if I keep pulling this down, decreasing it. So what it says is that increasing the phase margin for a little while at least is good for this system. And so if I move this up to a little bit more, maybe right about, let's call it right there. All right, that's 30.5 degrees phase margin, so right around there. So now if as long as the gain is bigger than 0.67, then we will achieve our phase margin. So now we've got this criteria. It needs to be bigger than this, but it also needs to be less than that 0.73. So that's actually our window, that range of gains between 0.67 and 0.73, or about those numbers, is exactly when the system with proportional control will achieve gain margin greater than 5 dB and a phase margin greater than 30 degrees. Coming back into our slides here, we can see on this very busy diagram that I've pulled out all of those points that are relevant here. That's just for a little bit of documentation. But primarily, if we move on to this slide, now we can see that summary of all of those things. So again, we had gain margin that was already read off. We had 3 0 dB crossings that led to 3 phase margins and indicated at these different values. And we take the smallest phase margin. So 36.7 degrees is the smallest, and so that becomes the most important. And so that's the one we report. And then again, we adjusted, by adjusting the gain around, we could identify that about 0.7 was the cutoff for as soon as the gain gets bigger than that, we no longer satisfy our gain margin. But if we make our gain too small, we make it smaller than this 0.64, then we end up not achieving our phase margin. So this range between 0.645 and 0.71 is the range of gains that satisfy these two gain margin and phase margin criteria.